So in this example, what we're going to do is look at a parametric equation where you've got like a t equals something and or you have y equals t equals something and x equals t equals something, and so how do you take a derivative of that? Well, there's a way to take a derivative of a parametric equation, and you have to take a derivative with respect to y and take one with respect to t, and when you divide those two guys, the dt part cancels out. It's all math. So if you'll just notice right here, if I have y equals or x equals or y equals, so if I have let's just go with x equals something t and y equals something t, then when I take derivative of that, I'm going to have dx dt, and when I take derivative of this one down here, I'm going to have dy dt. And so when I put the derivative of y, dy dt over dx dt, I end up with dy dx. And keep this in mind. If you'll notice, when you're working this out, I need dy dx in the numerator. Well, this is just like slope. So on the top, this is my change in y, and on the bottom, this is my change in x. So I've got to have that slope part to do the parametric equation correctly when I take the derivative. So how does it work? Well, it works like this. Find the line tangent to the right-hand hyperbola branch defined parametrically by x equals secant t, y equals tangent t, from negative pi over 2 to pi over 2. So how does all that work, you might ask? Well, here's how that works. What you're going to do is find dx dt. So we're going to find dx dt. And when we find dx dt, we're going to get, let's see, secant t tan t. And we're going to find dy dt. And when we find dy dt, that's the derivative of the tangent part then, so that's going to be secant squared t. And then we just do our division, secant squared divided by secant t tan t. So what we're going to end up with is the y part on the top, so secant squared t, and then the x part on the bottom. And so we'll put x in this mustardy color. So this is going to be secant t tan t. Okay, and what this really is, this is dy dx. That's what dy dx equals. Well, we can reduce this just a slight little bit, and we end up with secant t over tan t. Okay. And then if you think about this, if I've got secant t over tan t, tangent, this is like saying secant t cotangent t. And the cotangent, if we think about what these guys are now, because we can clean this up even more, 1 over secant, or secant is 1 over cosine t. Cotangent is cosine t over sine t. And so the cosines cancel out, and I'm actually going to be left with 1 over sine t, which is cosecant t. That's my derivative, okay? So, find the line tangent to the right-hand hyperbola branch defined parametrically by, and then it gives me this thing. Well, that's going to be my tangent line, my tangent slope is going to be cosecant t. So dy dt is equal to the cosecant of t. That allows me to find my slope at any point along this line. Okay. Well, what about if we've got a point? Let's say we've got a point that is square root of 2 over n 1, and let's say we're interested in t equal pi over 4. Okay. So if I know what my slope is, then I can find the slope of my line by putting pi over 4 in for the cosecant of t. And when I do that, this becomes the cosecant of pi over 4. And what does that equal? Well, that's equal to 2 over the square root of 2, which reduces to the square root of 2. And you can use a trig table to get this answer. And so this is the slope then of my tangent line. And if I know a point on the line and the slope of a line, can I write the equation of the line? And the answer is yes. My equation on this guy is going to be y minus the y coordinate equals the slope times x minus the x coordinate. And that's all you need to do on that guy. There's using a parametric equation to find a derivative, and then taking that and finding the slope at a specific point.